Okay. So when it comes to naming acids, Emma, can you turn off the light? There's two rules. There's two different ways to name them. One, you have the binary acid. In binary acids, it's only two elements, or two ions. One is hydrogen. The other is a monatomic ion. You find it on the periodic table. It's a lone element. The key here, guys, is that there's no oxygen in these. That's the other acid. In rule 1, you begin the name with hydro. Number 2, you use the root name of the second element. Number 3, you end the second element's name with IC, ick. And number 4, step 4, the second word is acid. That's it. So let's do 5 practice ones here, then we'll do oxyacids again. So practice number 1, P1. I want you to name hydrogen and iodine. So let's put it together first. Let's figure out the actual formula. You need to put hydrogen and iodide together. What is the charge of a hydrogen ion? +1. Very good. I like the participation already. What is the charge of an iodine ion? So what ratio do they go together? That is correct. So the formula would be HI. Now, if I told you that this is in an aqueous solution, which means that if you put HI into water, it will dissolve, that tells you it's an acid. So first off, guys, do you see any oxygen in this? No. So you're going to name it according to binary acid rules. That should be the dead giveaway. If there is no oxygen, you are to use binary acid rules. All right. So you start. What's the first one? Yes.
What if there is hydrogen?
Then you do the oxyacid rules. We did those yesterday. We're going to recap that after this. Okay, so this is where you started to slow down and got really shy yesterday. If there's no, just go by the steps I wrote above. What's the first thing you need to write down? Hydro. What is the root of the second element? Iode. And then what do you end it with? Hydroiodic. And what's the second word? That's it. Done. Hydroiodic acid. Hydro is the first part. Iode is the second part. Ic is the third part. Acid is the fourth part. Okay, good. Let's do another one. Practice number 2. Hydrogen and sulfur. Okay. What is the charge of a hydrogen ion? +1. What is the charge of a sulfur ion? -2. So how many hydrogens do you need? You need 2 of them. So that's going to result in H2S. And if I told you it was in an aqueous solution, you know that it is an acid. So what do we start off with? Hydro. Now, sulfur is a little weird. And you guys learned this yesterday. You're not going to say sulf. When it comes to sulfur, you say the whole element. This is unique to sulfur. So we're going to say hydrosulfur. And what do we end it with? Ic. And last part? Hydrosulfuric acid. That's the name. Any questions? Okay, let's do practice number 3. We got 3 more in our bag of tricks. Hydrogen and phosphorus. What is the charge of hydrogen? Positive 1. What's the charge of a phosphorus ion? Negative 3. So how many hydrogens do you need? You need 3 of them. So the formula is going to be H3P. What do you start off with? Hydro. And for phosphorus, the root is phosphor. And what do you end it with? Ic. And what's the second word? That's it. Hydrophosphoric acid. Yeah.
Is there an AQ up to here now?
Yeah, I didn't write that, but good call. How are we feeling? Arshawn?
If we're like writing the acid and like we get like the root of the single word off like a little bit, is that okay?
I'm not gonna. As we get further down the road, I'll expect more. But as of right here and now, I'll be a little more lenient. You guys are just learning this. All right, 2 more. Hydrogen, and let's see. What do I want to do? I'm looking at the periodic table there. Nitrogen. Okay. What's the charge of hydrogen? Charge of nitrogen? What's the ratio? H3N. Okay, what do you start with? Hydro. What's the root of nitrogen? Nitro. Or we'll say nitro. Yeah, this is what Arshawn was alluding to. If you get it off by a letter or two, I'm not gonna kill you. Hydronitric acid. All right, let's do one more. This is the acid that is in your stomachs. That's why, here's a fun fact. When you throw up and your throat burns and your mouth burns, it's because you have a layer of mucus in your stomach. It protects your stomach from the acid, but you do not have this layer of mucus in your esophagus or in your mouth, which is why it hurts, it burns. That's how people get heartburn. The reason they call it heartburn is because your esophagus travels right in front of what organ? Heart, or right behind it. So it's not that your heart's on fire, it's just that your esophagus goes right past your heart, and your esophagus does not have the lining of mucus like your stomach does, so it can burn your esophagus. All right, hydrogen is positive 1, chloride is negative 1. That's going to be a 1-to-1 ratio. This should be hydrochloric acid. And that is the acid that is in your stomach. It digests proteins. Okay, so are there any questions with how to do the binary acid naming scheme? Feeling better about it than you did about 48 hours ago? Okay, you guys sound like you have a little more confidence. All right, let's go into oxyacids. Okay, the first thing that you have to do, identify if oxygen is present. Okay? And I also want to tell you there's no hydro prefix, okay? No hydro, not with an oxyacid. An oxyacid is composed of 2 ions. One is hydrogen. 2 is typically a polyatomic ion with oxygen.
What is an oxy in that? Or just
Yeah, an oxyion. Or oxyanion. So, rule number 1. Identify the oxyanion. An oxyanion is the negatively charged ion that possesses oxygen within it. Number 2. Identify if the oxyanion ends with ITE or ATE. Ite or ate. Number 3. If it ends with ITE, you're going to replace ITE with OUS. If it ends with ATE, you're going to replace it with IC. And then step 4, second word is acid. There is no hydro with these. Yes, Nicole? You're going to keep that. If it's per or chlor, you're not going to do anything with that. You're just going to keep it there. Yes. Yes. Yeah.
So oxyacids always end in a polyatomic ion.
Yep. All right, so keep those rules out and have your lists out. Here we go. Let's do 5 practice, and we're going to get on to new stuff today. Practice number 1. Hydrogen and phosphate. I told you yesterday when I was in high school, I was for a summer job. I was a summer camp counselor, YMCA. They gave me all the older kids, the 5th graders, and I said, you guys want to see something cool? You put an earthworm into soda, it'll dissolve. Why does it dissolve? Because there's phosphoric acid in it. So if you see that hydrogen has a positive 1 charge, do you remember what the charge of phosphate is? -3. So what ratio do you have to have? You have to have 3 hydrogen to 1 phosphate. So this is going to be H3PO4. And it's going to be aqueous. So we need to come up with a name. So this is called phosphate. Does phosphate have oxygen in it? Yeah, so we have to name it according to the oxyacid rules. It ends with ATE. So what do you replace ATE with? Ic. Now we don't say phosphic. This is a unique one. You say phosphoric. And the second word is acid. If you look on the ingredients to Coca-Cola or Pepsi, it says phosphoric acid. When I was in college, my roommate liked to play golf a lot. He would wash his golf clubs with soda because it also dissolves rust. When I was in high school, I had a rusty tailgate in my Jeep. And I was like, Dad, I got a leak in my Jeep. It's like making the tailgate rusty. What do? He handed me a steel brush and a bottle of phosphoric acid. He says, scrub it out. So that stuff dissolves rust and you drink it. I want to second guess it. Next, hydrogen and sulfate. So hydrogen is a positive 1 charge. Do you remember what the formula for sulfate is? It's SO4 with a -2 charge. How many hydrogens do you need? 2. So it's going to be H2SO4. It does possess oxygen. So let's go into naming it according to the oxyacid rules. It ends with ATE, sulfate. So we're going to change to sulfuric. These are the only 2 that really have an exception to it. I wanted to get these out to you guys. So that's nitric and then acid. sulfuric acid. That stuff is in batteries, like car batteries. Yeah,
Could hydroxide become an acid?
that's a base. Okay, let's go to a third example. Hydrogen, you're going to need to look on your list on this one. Hydrogen and sulfite. Now, you all know hydrogen is a positive 1 charge. What is the formula for sulfite? SO negative 2, 3. Think about what you just said.
SO, the charge is negative 2, just 3.
SO3 with the negative 2 charge. Now, I want to give you guys a little suggestion here. Pay attention to this. I taught you this before the break. What is the only letter that separates sulfate from sulfite? A and I. The one that ends in ATE has one more oxygen than ITE. Know that. The polyatomic ion that ends in ATE has one more oxygen than the ion that ends in ITE. Okay, so if I told you that sulfate is SO4 with the negative 2 charge, what must sulfite be? SO3 with the negative 2 charge. If I told you phosphate is PO4 with the negative 3 charge, what would phosphite be? PO3. It's just one less oxygen. Don't overthink it. If carbonate is CO3 with a negative 2 charge, what would carbonite be? CO2 with a negative 2 charge. If chlorate is CO3 with a negative 1 charge, what is chlorite? ClO2 with a negative 1 charge. And last one, if nitrate is NO3 with a negative 1 charge, what is nitrite? NO2 with a negative 1 charge. So the one that ends with ITE just has one less oxygen than with ATE. Okay, so at what ratio will hydrogen and sulfite balance out? 2 to 1. So it's going to be H2SO3. This is sulfite, so what do we change it to? Sulfurous acid. Let's do a couple more. Hydrogen and chlorite. You know, hydrogen is positive 1. Look at your list. What is the charge of chlorite? It is ClO2 with what? Negative 1 charge. So what ratio do they balance out? 1 to 1. ClO2. Okay. This ends with ITE. So what do you replace ITE with? So it's going to go from chlorite to chlorous acid. The last one. This is nitrate. What is the charge of nitrate? How many hydrogens would it take to balance it out? HNO3. It's called nitrate. So how do you change its name to an acid? Nitric acid. Not ATE got switched to IC. And over here, ITE got switched to OUS. Any questions? No? Okay, let me give you guys, let me tell you what your homework is before the end of the period so I don't have to keep you after the bell. So let's hop over to the internet. During my lunch, I'm going to make this an assignment, but it's already online. If you go to your Canvas page, if you scroll down to Unit 7, Molecules, Click on that, go to assignments, and it says naming acids worksheet. This is going to be your homework. It's going to be due by midnight. You see all these names? You need to give me the formula. You will need to refer to your list that you should all have out right now to help you. There will be some that you do know. There will, like phosphoric and carbonic. And then there will be some that you may not be familiar with, like formic or boric or perchloric. And then on the next page, you have the opposite. I gave you the formula. You have to give me the name. I want this turned in by midnight tonight. So by the time I'm done with my lunch period, which is fifth period, it will be under assignments. It'll be called Naming Acids Worksheet. Any questions with that? Yeah.
You want us to turn it in?
I want you to submit it on Canvas, but I also want you to bring it to class tomorrow so that we can go over it so you guys can get any questions you may have answered and get all the right information provided to you. All right, let's go into what I have for you today. Today we're going to do molecular structures. And resonance structures. All right. Okay. So there's a lot of different molecular structures out there, and I'm going to have a kit out here to build a few for you. You guys did this the Friday before break. So there are various models used to represent and depict the shape of a molecule. First one is you could just have the molecular formula. So let's say I want to do phosphorus trihydride, pH 3. That would be the molecular formula. Number two, you could have the structural formula. Number three, you got the space filling model. That would be each of these blue ones is hydrogen, 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 and the red one is phosphorus. It's supposed to be three-dimensional. It's a little hard to see it from this perspective. Number four is the ball and stick model. It's kind of what you guys did on the Friday before break. So for phosphorus trihydride, you would have the phosphorus here, hydrogen, hydrogen, and hydrogen. And for the Lewis structure, it would look like this. Now, the structural formula is basically the Lewis structure without the valence electrons on the top. We're really not going to do that one too much. So there's just multiple ways to actually to draw the same molecule. So what you guys basically are going to do for me is I want you to do some practice. So let's do example number 1. I want you to do the molecular formula. So I want you to do 1, 3, 4, and 5. Don't worry about 2. 2 and 5 are practically the same thing. For ammonia, NH3. If you could please try to do NH3 according to the molecular, I just gave you the molecular formula, so 1 down, 3 to go. I want you to try to do the space filling model, the ball and stick model, and the Lewis structure. Yes, Arshan.
The space filling model. You just write.
You just basically take the bond, take those lines that represent bonds, you take them out of the picture.
Okay.
You put them right up next to each other.
Can you still label it like you did on the
Sure. Yep. All right. Here's something close to what you should have. Okay. Here's, if you look up here at me, this is ammonia. Now, do you remember this thing, this big bubble on top? Do you remember what that represents?
Like an unshared pair.
It's an unshared pair. Very good. So the way this actually looks, guys, there's 2 different molecular shapes. There's one that looks like this, and there's one that looks like this. The reason why this one is the correct one for ammonia is because this unshared pair is forming a very powerful electrostatic repulsion. I told you before break, it's kind of like that they resent not being part of the bond. So the fact that they are not part of the bond, they have a very strong repulsive force. So they're basically forcing down the other bonds away from them, as far away as they can get. But they also have to stay as far away from each other as possible. So that is called a trigonal shape. And we're going to go over all the different shapes that you need to know for this class in a moment. Here's an easier one I think you may have. I want you to do the same with carbon dioxide, CO2. I just gave you the molecular formula. Try to do the rest. See if you remember how to do CO2. There's a little trick to it. Okay, so I have them all up on the screen. This is the molecular formula. This is a space-saving model. This is the ball and stick model. And this is the Lewis structure. The structural formula would be the Lewis structure just without the electron pairs. This is called a linear shape because it's a straight line. All right.
For the space saving, does it matter? It's like, should it be all circles?
Should it what?
For the space saving model, should they all be circles, or does it not matter what shape they are?
Yeah, the space saving, they all look like these, just without the bonds. Yes, Nicole.
For the Lewis structure, why wouldn't the unshaped pairs be more like farther away from the ball?
Because you're just trying to make it, there's really nowhere for them to go because the double bonds are stronger. They're able to resist more of that pull. Yeah, if they were to tilt a little to the right, they would get closer to each other. So this is also a pi bond. So they have this big force here and here. And if they try to shift a little to get closer to each other, they're going to start to interfere with each other. That's as far away from each other as they can get. All right. So what I would like to do with you guys now is I just want to show you the shapes. There's about 6 of them that you need to know for this class, and it's better if I look them up online rather than try to draw them. You can draw them in your notes. So I'm going to switch over to the internet, and I'm going to go to Google. And if you're watching at home on YouTube, I'm going to switch it over in a sec. I'm going to type in molecular shapes. Okay, so let's see, which one do I think looks good for you guys? Let's see. This one looks good. Here we go. Perfect. Okay, so let me switch over everybody watching at home. Where's the image? Oh, that stinks. One sec. I got this. There we go. Come on. All right, let's zoom in on it. Perfect. Okay. All right, cool. I want you to copy those down. And then I'm going to draw them more on your notes. So you have linear, nonlinear, which is bent like water. You have trigonal planar, which looks like a triangle, but it's flat. You have pyramidal, which is like a triangle, but 3-dimensional. You have tetrahedral, which is 4. You have square planar, which is going to be flat. You have trigonal bipyramidal, and you have octahedral.
You want to start the degrees?
Yes. Yeah. And so one thing that you're going to have to do is you're going to need to be able to identify a shape by looking at it. So if I showed you the bottom right corner, you need to be able to tell me, is that octahedral? Is that pyramidal? What's good? So I'm going to make a few shapes over here while you guys are doing that. And I want you to tell me what it is. Okay. Finish up. Okay, I'm going to switch Zoom so people at home can see. So let me turn that on. All right, guys, let's turn on a light. I want you to, as a class, just tell me what shape am I holding up. This is ammonia, NH3. What is this? Arshawn? Pyramidal, yes. What is causing the bonds to be forced down? The valence shells that are up here somewhere. If there were no valence electrons up here, unpaired shares, what shape do you think it would be? It would probably trigonal planar. The plane means flat. Yeah.
How does that happen with the trigonal planets? What if there always be unshared pairs?
There's some that are an exception, like when boron is BH3, boron would only have three hydrogens bonded to it, so it would be flat. There's some exceptions to the rule.
So is that just like you just need to see this?
Yes. Yeah. All right. So this right here is going to be pyramidal. Here's carbon dioxide, the gas that we exhale. What shape is this? That's linear. There's no valence electrons pushing it down, so it's going to be just a straight line, 180 degrees. This is water, H2O. What's that? Bent. You can say bent model. What is forcing them down to prevent? What's preventing it from being like this? The unshared pairs on water is forcing those bonds down. Here's methane. This is swamp gas, and this is fart gas. This is tetrahedral. Yeah, tetra means 4. So there's 4 bonds. And then, here's one you might be a little confused on. I'll explain it. This is sulfur hexafluoride. What is that? Octahedral. Now, you might be thinking, what does octa mean? And how many are here? 6, right? So what the heck? I'll draw that for a second. I'll tell you what it is. But this is going to be octahedral. Okay? So before I go any further, how about I draw that for you and tell you exactly why octa only has 6. I can try to draw that for you. It's going to be 3-dimensional, so it might be a little tough. Okay. All right, so let's see if I can draw this. Trying to draw 3D on a 2D thing is not going to be easy. 1, 2, 3, 4, 5, 6. Okay. Let's see if I can do this. You want to hit the light, Emma? So it has 8 faces. 1, 2, 3, 4, 5. So it's hard to draw on 2-dimensional. So let me try to hold it like this. You guys see, watch this. Just look up here. From here to here to here, that's 1 face. Here to here to here, that's 2. Here to here to here, that's 3. Here to here to here, that's 4. Then you flip it, you do the same thing. 1, 2, 3, 4. It's like a diamond. So it's actually going to kind of look like this. So it's hard for me to draw 3-dimensionally like that, but it has 8 faces. That's why it's called octahedral. All right, what time is it? We have about 6 minutes. Let's do one last thing. Resonance structures. All right, well, class is almost over, so just go sit down. Okay, this is likely going to carry over into tomorrow. We're about 10 minutes behind where I want to be. That's okay. Resonance structures. This is where you have more than one correct Lewis structure for a single molecule or polyatomic ion. So let's try this. I want to see what you guys are capable of. It's probably going to take more time than what we have available. What do you call that layer in the earth that protects us from ultraviolet radiation? Begins with an O. The ozone. Ozone is O3. How many oxygens are there in the molecule that we call ozone? There are 3. So here's where the puzzle putting together person and you needs to really come out strong. There are 3 oxygens. I'm going to save this for tomorrow. This is just getting you set up for tomorrow. Here's what you're going to need to do. I want you to be able to figure out how to get all 3 of them together so that each of them has 8 valence electrons. We will do that after we have gone over your acids worksheet that is due tonight. Hear that, Adam? You have an acids worksheet due tonight. You need to watch today's video so you don't get left behind. So after we've gone over your acid worksheet to make sure you guys understand what you're doing, I'm going to help you with this, and you're going to see there's more than one correct Lewis structure. See if you can try it at home. This is a good puzzle. If you like Rubik's Cubes and you like putting things together, this is going to be up your alley. I want you to try to see if you can get all 3 oxygens to have 8 valence electrons. And there is more than one correct Lewis structure. This is called a resonance structure. We will do that tomorrow.